Flexibility is often what separates the good tools from the great tools. Sure, when something is perfectly optimized for a specific task and it works flawlessly, it's very satisfying. And it can certainly be a fun challenge to get that tool to that optimum state. But it can be equally, if not more difficult to design a tool in preparation for the unknown. These kinds of tools are especially valuable where low production quantities are concerned, like in my shop. In the past, I've made do with custom single-use fixture plates that I've made for specific jobs, but the universality of a mini pallet system would really suit my doings much better. So I decided to make one myself. Mini pallet, universal fixture plate, tooling plate, all different names for the same basic thing. A plate with a whole bunch of holes in it that can accept a variety of different hardware that will hold parts during machining. Since the configuration of this plate could be anything, and the different types of hardware are almost limitless, this design could get complicated really fast. So I'll just start with some basic pieces that I think would be the most useful for my shop. The plate itself will be made from a piece of 2124 aluminum. Other than just being what I have on hand, it does have some slight advantages over common alloys like 6061, namely a higher yield strength and hardness, which should in theory lower my risk of denting and nicking the mounting surface. The hole pattern will consist of both threaded and reamed holes that will give me plenty of options for installing clamps and locating pins, and I'd also like to be able to set this up in a variety of situations in the mill. So a couple of counterbore holes will make this mountable with T-nuts to either my rotary table or directly to the mill table itself. At 9 inches by 12 inches, this is a bit large for clamping in the vise though, so I'll make an optional subplate that will fit between the jaws. And in the event I want to mount this plate at an angle, a separate pivot bar attached along one edge will give me the means to do just that. I'll use a few off-the-shelf screws and pins to act as locating features, but I'll also make some slotted adjustable bars for positioning against material edges. Including both flat and round ends should take care of most geometries I might have to clamp to. I'll also take a stab at some low-profile eccentric edge clamps in the common Mitee Bite style. Chris at ClickSpring did a video on these recently, and the simplicity of them really caught my eye. The key feature of these is an eccentric screw that applies a lateral force on the clamping element to keep the part secured. And for the clamping elements themselves, I'll include both flat faces as well as a round side for the added flexibility. There is some other tooling I can envision needing at some point, but considering I'm really bad about scope creep, I'm going to cut myself off here. Honestly, I think I'll have my hands full with all this, especially the pallet itself. So I'd better get started and tackle the most complex part first. The raw material I'm starting with is nominally 9 by 12 inches, which poses the first problem in that this won't even remotely fit into the vise, which means this project just got a fair bit more complicated, but I like a good challenge. To start, I'll place some scraps of aluminum tooling plate directly on the table to elevate my pallet material up off the surface. Then I can clamp this down from each side. These will get in the way of milling the ends, but I have a way around that. Since I only left myself the bare minimum material to remove from the sides, I'll tram the plate with the mill using the dial indicator before tightening everything down. To make the cuts, I'm going with this 10 flute 1.5" end mill. I've never used it before, but something is telling me it will leave a nice finish, which is what I'm hoping for. Yeah, I'd say that's pretty nice alright. That's practically a mere finish. I have just enough travel to reach the front edge of this plate, so I'll knock that out while I'm here as well. While I can't do the sides quite yet, I can at least mill them partially. This seems silly, but for the next operation I need a good corner to go by, so I'll take a short pass and leave about 10 thou extra on each side to clean up later. With a nice clean corner to reference, I can edge find on this, then move on to drilling and counterboring the 2 mounting holes from the design. These will let me mount directly to the mill table and make the following operations much easier. Alright, that wraps it up for this setup. But this setup was just to get me set up for the next setup. And before I can do that, I need to double check the tram of the mill head. In this case, I want as much accuracy as possible. So I'll use my dial test indicator, which is accurate to a 10,000th of an inch. For this roughly 9-inch arc, I'm seeing a difference of 7 to 9/10. That's pretty darn close, but I think I could do better. When trying to target accuracies at this level, it really becomes a lesson in patience. Make a slight adjustment, see how much the measurement changes, and repeat. until you're either happy or completely fed up. In this case, looks like I got it pretty good. I'll mount the plate back on the spacers, this time dropping bolts through the holes I just drilled and screwing them into T-nuts below. This doesn't quite align the plate to the accuracy I need, so I'll tram along one of the finished edges much like before and snug this down tight. I'll take a light mill pass along one of the edges, then measure between that and the partially finished edge on the opposite side to figure out how much more I need to go. The idea here is to keep the 2 holes I already drilled in line with the grid pattern I'll drill later. Repeat this on the final side and all 4 edges are ready to go. Time to move on to the top face. And it just so happens I have the perfect tool for this. I made this giant fly cutter in my last video specifically for this operation. It's adjustable in diameter so I can increase the cutter's swing to wider than the material width, and it's also adjustably counterbalanced to minimize vibrations. I'll spray down the surface with a little WD-40 and this bad boy is ready to do its thing. When I built this fly cutter, some people were concerned about parts flying off of it. Curious myself, I did a little math to figure out how much of a catapult I created here. For a 10-inch diameter cutter running at 600 RPM, the fastest a part could possibly launch off of here is a whopping 18 miles an hour, or basically a gentle toss. Not to be ignored entirely, but also nothing to make me tremble in my work boots. I must say that first pass looks pretty good, but I see some room for improvement. All of the cutting marks are going in the same direction, rather than crisscrossing like in this region. While all one direction looks nicer, by my understanding it's indicative of an outer square spindle, and means that the surface could be slightly dished. But since I know the mill was trammed very well, I suspect something else might be at play here. Due to the steep rake angle of the cutter, it pulls down slightly as it engages with the material. And because the wheel is made from aluminum, which has a lower modulus of elasticity than steel or cast iron, it seems to be flexing down more than I'd really like it to. It's too late to dive into remaking this fly cutter from a stiffer material, so instead I'm going to try this again but with a much lighter pass around 1 thou. And this time taking a spring pass back in the opposite direction without changing the depth. Interesting, this time there was no cross-hatching at all and the pattern matches the trailing edge of the spring pass, meaning it was engaging on a surface that was basically cut 3 times already. I wonder if instead of the wheel being flexed down, it's actually flexing up, and that last pass basically rubbed the surface smooth. This may be pretty flat after all. Wow, a light test with a straight edge shows not even a sliver coming through. I'm actually pretty pleased with that, so I'm going to move on. Now I don't know anybody that doesn't love a good chamfer, so I'll take care of these edges quickly. Yeah, that looks nice. Okay, enough procrastinating. Time to move on to the more numerous details. There are 165 holes in this plate, and each one takes about 4 operations. Wow, when I started this project, I didn't think I'd be essentially drilling almost 700 holes. I hope the mill is up for this task. I'll start like I always do, with a center drill. Rather than take this all the way down to the tapered portion, I'm essentially just spot drilling each location. There really only needs to be enough material here to center the main drill. Alright, that's 171 operations down. You might recall that the hole pattern is alternating tapped and reamed holes. I'll do the tapped holes first and mark each of these just to make sure I don't get them mixed up. Also, I really don't want to drill into the mill table by accident, so I set the quill stop well above that surface. And better yet, combining this with the automatic quill feed means it automatically disengages and lifts up out of the hole, saving me a few movements. Sometimes it's the little things. 250 operations complete. I again use the quill stop to set the depth of the starting chamfer on each of the holes. This may be considered somewhat of a frivolous feature given how many holes there are, but I couldn't resist. And by this time I'd really started getting the rhythm of traversing the table to each hole location quickly. To tap the holes, I'm using a spiral point tap to push the chips out the bottom of the plate to the gap underneath. This lets me power tap each of the holes, saving a ton of elbow grease. A spiral flute tap would be even better for this, but here I'm just using what I have. In either case, I have to be extra careful to stop and reverse the spindle before the tap hits the table. Having the quill micrometer is especially helpful for this, as I can see zero approaching in reverse direction before catastrophe strikes. I think I just jinxed myself. The mill no longer wants to rotate. I can see it's trying to, but it's sort of just locking itself in place. Almost like it's not getting full 3-phase electricity. Actually, I'd bet that's exactly what's going on. See that static phase converter? Yeah, that little red light isn't coming on anymore, and it definitely should be.
Well, there's your problem.
I think it's safe to say this thing is toast. The capacitor inside has completely blown its guts out. And reflecting back on it, I think it's my fault. When I was power tapping, rather than waiting for the spindle to come to a complete stop before reversing, I was flipping the switch to speed up the operations, which apparently was too much load for this 30-year-old capacitor. So consider the lesson learned. I won't be doing that again. I do have a couple other phase converters laying around, but unfortunately they're all rated for much higher than the mill's power requirement, meaning they won't work. Believe me, I already tried. So the mill is basically dead in the water. But there is a silver lining. I've been wanting to upgrade the mill to a VFD for quite some time, and I think I just found my opportunity. Consider it a done deal. There is just one issue. It won't arrive in time to finish this video. I know, real bummer. But I'm not about to leave you hanging like that. While the VFD will take some time to get here, I can get a replacement capacitor delivered in a day for $7. While I wait for the capacitor to arrive, I do have one other machine that's still in operation, so I might as well make some headway on all the turned parts. I'll start by turning the pivot bar down the size. I've got quite a good length of some 6061 aluminum that would be perfect for this. It may just be a little awkward to cut the length. I'll take this stock through the all too common operations of facing, center drilling, and bringing in the live center. Then I can move on to the diameter. My goal is to get this bar as cylindrical as possible since it will be the primary alignment surface once it's coupled with the pallet. To help with this, I've cut this stock about an inch long so I can turn the whole length I need in one pass. Once in the neighborhood of the final diameter, I'll take a lighter tooth thou cut, then measure to see if there's any taper in the part. Only about a thou, but enough that I feel compelled to correct this, which I can do with a slight adjustment of the tailstock. In a previous video, I went through the whole process of leveling and aligning this lathe, including the tailstock. But for a whole gambit of reasons, there are some minor adjustments I have to make on the fly like this when precision is really important. After another light cut, it looks like I've taken care of that taper. Only about 1/10,000th variation, which I'm pretty pleased with. Now I can take this down to the final diameter, drop a nice chamfer on the edge, part this off, then face and chamfer the opposite side as well. With the turning complete, this part joins the queue for the remaining mill work. I'm still waiting on the capacitor, so I guess I'll make some headway on the hardware. These button screws for the clamps need to have their heads turned to an eccentric profile. And to do that, I'll be using this tapped round slug I made at some point in the past. I'll mount this on the 4-jaw chuck to true it up concentrically. And once there, I'll adjust 2 opposing jaws to shift the slug for the 20 thou eccentricity I need. Then I can thread one of the screws in and start whittling the diameter until I'm right at the dimension. That's one screw down. To finish the rest, I can simply leave the cutter at this depth, then just bring in the remaining screws and take them to diameter in one pass. 6 should be enough for my needs. Alright, I'm running out of things to do and I still don't have a capacitor. I could work on the eccentric clamps themselves, which would need counterbored holes in the centers, but I'd really prefer to mill all the flats on this piece of bar stock first. You know, a lathe is more or less just a mill that fell over. I have an idea. That's one part of the equation. Now I need a way to hold the material somehow. And lucky me, it fits perfectly in a tool holder. I just have to adjust the height a bit to get it close to the tool center line, and for good measure might as well tram it square with the spindle. I honestly can't think of a reason why this wouldn't work, so I'm going to send it. Well, I think it goes without saying that that went great. Really no visible difference than if I had done this on the mill proper. To cut the other 2 flats, I can simply rotate the stock in the tool holder and use a bevel protractor to align with the face I just cut. Then tighten everything down and mill the next flat. Repeat this once more and the bar milling is complete. That's 3 flats made not on a mill. I'd call that a win. Now I can finish these parts up using the lathe in its proper form. From here the operations are far more straightforward. Face the end, drill the through hole for the screw, switch to an end mill to form the counter bore, drop a slight chamfer on here, then just part it off. Repeat that 5 more times and I've got myself a nice little army of clamps ready to go. The pallet might not be finished yet, but there's at least enough going on here that I can give these a test. Wow, that actually holds a fair bit tighter than I would have guessed. And that's only with one clamp. Consider me impressed. But that's not the only good news. The all-important package just arrived. Talk about impeccable timing. There's the capacitor. 2 actually, just in case. And I splurged a little and bought a new soldering iron. This should theoretically be a pretty easy fix. Just gotta clean up the guts of the old capacitor, melt away the soldered connections for the 2 connecting wires, mount the new capacitor in place of the old, then resolder the 2 wires back in place. Good as new. Let's get this mounted and reconnected to the mill to see if that did the trick. Sweet, sweet victory. Everything is still set up from before, so it's just a matter of picking up on the tapped holes where I left off. That's 405 operations down, and I'm past the halfway point. Next, I'll work on the holes that will accept the dowel pins. For these, I'm using the common practice of drilling 1 imperial size below the final reamed hole dimension. And naturally, these all get chamfers as well. Now to ream the holes. The pins I ordered are nominally 5/16 diameter, but are precision ground undersized by 1 to 3/10. So by using a reamer right at 5/16, this should leave me a nice locational clearance fit. Yep, that's pretty much perfect. Alright, that's enough. Back to work. This brings me to the final 3 holes for the pivot bar mounting. Now you might be wondering why these holes are countersunk rather than counterbored. And there's actually a good reason. I want the heads of these bolts to be what holds the pallet in location on the pivot bar. This will actually make a bit more sense once I get that pivot bar complete, so hold tight. Alright, that's 165 holes and 657 operations knocked out. That might be one of the longest setups I've ever had, even excluding the downtime from that little capacitor incident. I still have one more side to finish on this plate, but I can't do that without a good way to hold it. So I have to put this on the back burner one last time while I make the sub plate. Fortunately, this is a pretty straightforward part, so I should be able to knock it out rather quickly. I'll remount and retram the vise, since this part will actually be small enough to fit between the jaws. No surprise there, since that's literally the only purpose of this sub plate. I'll first clean up the free edges on either side with the same finishing mill as before. Then swap to the fly cutter to clean up the top face. Still just as good as the earlier attempts. Those 3 operations have left me 3 square and flat faces I can count on. So from here I can flip the plate over and rotate it 90 degrees in the vise. Then fly cut this side as well. After side milling the final 2 edges square, I'm really interested to see how flat this actually came out. So it's over to the surface plate. Sweeping across the direction of travel, I'm getting a slight dip about half a thou in the middle. This is likely the dishing effect I mentioned before from a slightly off square spindle. Moving along the direction of travel, the deviation is a bit more, but still within a thou along the length. With the rise near the middle, I can only suspect that this is a result of the mill's table weight shifting as the parts traverse under the cutter. Given that the weigh gibs are still pretty well adjusted, I can't imagine that there's a whole lot I can do about this issue. I am, however, going to take another stab at tramming the mill head. This may be a complete waste of time, but when there's an avoidable source of error, I simply can't ignore it. I think I got it a hair better that time, so I'll take another light pass with the fly cutter on each side, then hop back over to the surface plate to see how it came out. That's actually a fair bit better. Only a couple tenths deviation across the direction of travel. Still some variation in the other direction, but all well within a half a thou across the whole face. Which is pretty good in my opinion coming from a knee mill like this. Alright, with that itch scratched, it's time to knock out the rest of the plate. First, chamfers all around, then the 4 counterbored holes in each corner. And that's it. One sub plate ready for its first job on the pallet proper. Which is of course fly cutting that last unfinished face. Oh, and I can't forget these. This wasn't part of the original plan, but there is one last thing I realized I need to do to the sub plate. There's currently nothing other than 4 screws locating these 2 plates relative to one another. Here in the vise with the connection screws loose, you can see that there's about 6 thou of wiggle room, and that simply won't do. To correct this, I'll first tram the pallet square to the subplate below. Then tighten the mounting screws from underneath. Next, I can align on 2 of the locating pin holes, and I can drill and ream matching undersized holes in the subplate underneath. And finally, I can drive 2 pins through it all. If everything worked out properly, I should be able to separate these two relatively easy. It's a snug fit, but that's exactly how it needs to be. One last thing before moving on is a final fly cut of the top face. If you remember, I've since readjusted the tram of the mill, so I just want to make sure that this surface is as good as I can get it. Nothing like a freshly fly cut plate. I could look at this all day, but I still have some loose ends to clean up. First are the brass clamping elements. Since my little test run, I realized these would be a lot more useful if the flats were varying distances from the center rather than all the same. Fortunately, this is a really straightforward change. I can line all 6 clamps up in the vise using the flats already milled as a reference, and just mill the new flats all at once. Then rotate and repeat. In this way, each subsequent face is 40 thou lower than the previous, which matches the eccentric travel of the clamping screws. So in essence, I've expanded the clamping distance from 40 thou to more like 200 thou. A little cleaning up and these are ready to go. The next loose end is the pivot bar. Fortunately, all the remaining work can be done in one setup. I'll start with a roughing mill to hog away most of the material forming the rabbet the pallet will mount to. And that's rabbet with an E, not an I. I'll then switch to a finishing mill to take both edges to final dimension. Last are the 3 tapped mounting holes. These correspond to the 3 countersunk holes in the pallet, and they're about 5 thou closer to the back vertical face than the ones in the plate. This way, when I bring the pallet in to mount it, that slight offset and the taper of the screw head actually forces the plate against the rabbeted face, keeping everything square. Now, when I tilt this plate up at an angle, I can count on it being square with the mill. Pretty neat, right? That's actually really secure. I don't know that I would hang off of it or anything, but for light mill work, it will do great. Alright, that's all the big stuff complete. I do still have the slotted bar stops left to make, but with that little electrical setback, I've simply run out of time to make them. I know. All in all though, I'd consider this a successful build. I now have one more fixturing option in my arsenal, and not only that, it's mountable on my vise, rotary table, and directly to the mill table itself if needed. Even though I wasn't able to finish up all the hardware, I do have enough clamping elements to take this for a test spin. And I think I have the perfect little project. Perfect. I inherited this machine shop from my grandfather, and through it, hope to share my journey of returning to my metalworking roots. It's truly amazing to me that one short year later, this is a result of sharing my love of this field. To all my followers and supporters alike, thank you from the bottom of my heart. And as always, thanks for watching, and see you next time.